Okay, so the next topic in our signal processing workshop is sampling. Now, as we all know that most of the realized signals, such as speech, that we generate using our vocal cords, or say musical instruments, or say the light that bounces off other objects and reaches our eyes, these are all in analog form, and we as humans can very well process these signals. But a digital machine such as computers or mobile phones, they can't do that. They can only process signals which are in digital form, in a binary form, which is zeros or ones. So we need some process of converting these analog signals into digital signals so that they can be utilized by our digital computers. So the process of discretizing these analog signals into different values of signal, different values at different intervals of time, this is known as sampling. And a sampled signal from these values can be generated back. An analog signal can be generated back from these samples using the process of extrapolation. Now, the sampling rate is the time interval between two samples, meaning if we take an analog signal and we take its samples, or we take the value of that analog signal at two different points, the time difference between those 2 points is the sampling rate, the rate at which the signal is sampled. And the sampling of a signal, or the conversion of the signal to analog from analog domain to digital domain, is done by a ADC. Now, ADC is a two-step process in which the first process is the sampler, in which it converts the analog signal into discrete time signal. An analog signal can have values at infinite number of time, say 1 second or 0.01 second or 0.001 second. But at, in the digital domain, this is impossible to demonstrate, impossible to process, because we have finite number of memory. We have finite size of a processor. The processor can process only a limited number of signal values. So we need to convert this analog signal into a discrete signal. What discrete signals are? These signals are defined at a particular intervals of time, say 1 second, 2 second, 3 second, 4 second, and rest, it is not defined for the rest of the time in between these two intervals. Now, the second step of this analog to digital converter is quantization, which is done by a quantizer. I'll show you what it is in a bit. First, let's see the different types of sampling. The first type of sampling is impulse sampling. Now we all know that what is an impulse. Impulse is a signal with amplitude 1, and the duration of that signal tends to 0, which means it is represented by an arrow of magnitude 1 at a instant of time, but the duration of that signal is almost 0. Now we take our analog signal, which is x of t, multiply it with this train of impulses, which is impulses at different intervals of time, and we get a signal y of t, which is again a train of impulses but of different magnitudes. But see, there's a problem with this. Impulse is a non-realistic signal because the duration of it tends to 0, which cannot be generated in a real life. So to solve this, the next type of sampling is natural sampling. What it does is it multiplies our analog signal with a periodic rectangular signal. Now rectangular signal, since it does not have uh, zero duration, it has a finite duration, so it is realizable. It is a real signal we can generate using our mod components and all. So when we multiply these two signals, we get a signal which is something like this. But see, there's one more problem here. If we take this sample still has different values at its starting and at its end, which does not solve a problem of discretizing it. It does not solve the problem of getting different values at different intervals of time, since at a given interval of time the value keeps on changing. So The final and the most widely used kind of sampling which solves all of the above problems is the flat top sampling. What flat top sampling does, it still takes the same signal, which is the analog signal and a periodic rectangular signal, but now it holds the value which it encounters first at this level. It stays at that same level when it multiplies these two signals. So here we can see the value does not change, it remains the same. So this is our one sample, and the sample can have a magnitude of something like this or this or this, but it's constant. It is, we can use it in a digital platform, we can, because it doesn't have a varying amplitude. All right. So the next step of our conversion of analog to digital signals is the quantization process. Now we know that our analog signal can have infinite number of values, can have an infinite range because it can have infinite number of decimal values as well. But again, we have limited memory, we have limited processing power, so we need to convert this we need to convert this discrete signal that we generated in the sampling process, and we need to map these infinite number of values to a finite set of values that our processor can handle. All right. So the process of doing this is known as quantization. So what does is it takes an analog value, which can be anything, and it maps it to a certain value in a finite set. It truncates the value, or it rounds off the value to the nearest value available in our finite set. All right. So but this quantization process leads to an error in our quantized signal or in our digital signal, and this error is known as quantization error, which is basically the difference between the actual signal and the quantization signal. This quantization error can be solved using using more number of values in our finite set, meaning that if we have more number of values that we can map our analog signal to, our quantization error decreases. All right, I'll show you how. So let's take an analog signal. This is a sine wave. All right, and we have a 8-level quantization system, which means I'll map my analog signal to 8 different values in our digital domain, which is 0 to 7, which is 8 different values. So this analog signal is then converted into something like this, and you can see that it is almost in the shape of that sine wave only, but now it has discrete values. It has 8 different kinds of discrete values, and let's see, this is the side by side comparison of our analog signal and the quantized signal. The blue one is the sine wave, which is analog form, and the red one is the quantized wave. And at the bottom, we see that I've generated a quantization error, which is the difference between these two waves. Alright, so we see that its magnitude can lie anywhere between minus 0.2 to plus 0.2. But now let's see what happens if I increase the number of values in my quantization, that finite set that I was talking about. Now I have a 16 level system. I have that same sine wave, but now I have 16 values to map that sine wave to. Alright, so I have 16 different levels of values. Here you can see, to which I have mapped this sine wave. This first I have converted into discrete signal, and then I have mapped it to this sine, to this 16 different levels, which is 0 to 15. Now this is the side by side comparison of the analog signal and the quantized signal. We see that it is much more closer than the 8 level system that I showed you earlier. And this also shows that we can see at the bottom we have a quantization error, which is the difference between these two signals. And now we see that the amplitude of the quantization error decreases drastically from 0.2 to just 0.05. You see, this is a very big decrease. This is the uh, increase in the number of levels led to decrease in the quantization error, and thus we have much closer representation of the analog signal in a digital signal. Now the next topic is the sampling theorem, which is also known as the Nyquist theorem. It states that if we have a band limited signal, if we have an analog signal that only has certain frequencies, it is limited. Alright, so we need to sample it at a certain rate so that we don't lose its, we say, the basic structure of the signal while sampling it. So if we sample it at a certain process and then we try to reconstruct that signal back from the samples, we should not lose any information. So to do this, we have this Nyquist theorem, which states that if f max is the maximum frequency of our signal, the analog signal, it contains a number of frequencies, and the f max is the maximum frequency which is there in our analog signal. So fs, which is the sampling frequency, should be at least two times that maximum frequency component. So let's say I have a sine wave, say, which has a frequency of 10 megahertz. So according to Nyquist theorem, I need to sample it at 20 megahertz so that if I try to reconstruct that signal back, it should not lose its information that it contained. Now here we can see I have taken an analog signal, which is again a sine wave, and these x's represents the period and the time intervals at which this signal was sampled, at which it was discretized. Now if my sampling rate is greater than the Nyquist rate, you see that I was able to generate this signal back. While from these samples I was able to generate this signal somewhat similar to the original signal. This is very similar. It may be distorted, but it has not lost the information in it. But what happens if our sampling rate is less than the Nyquist rate? Now this will lead to a phenomena which is known as aliasing. All right, what it says is if we don't do sampling at least the Nyquist rate, we may lose information from the signal, which means we may lose some of the frequency components from the signal, and some of the new frequency components may be introduced into the signal which weren't there. Now I'll show you this example. Here we take a sine wave and my sampling rate is very less than the Nyquist rate. See, now I've taken samples at a larger interval. So using these samples, when I try to generate my signal back, when I try to extrapolate this signal, these samples, and generate an analog signal from it, it is not only highly distorted, it has somewhat changed in its frequency as well. We see this, this was a sine wave of almost, say, the period is 2. All right, but here we see that it was converted. When I tried to change it from the digital domain, I went back to analog domain. I tried to extrapolate these samples. It gave me somewhat a cos wave which has almost a period of 8. So we see that we not only lost the we lost major information from our original signal. We lost the frequency, we lost the magnitude, we lost the kind of signal that it was. This was a sine wave. What we got back was a cos wave. So we need to sample at least the Nyquist rate so that we don't lose any information from our signal, we don't lose any frequencies, and it also avoids adding of new frequencies or appearing of new frequencies if we reconstruct that signal back.